In this lecture, we will study the global properties of spacetime. So in the last lecture, we have introduced the causal structure of the spacetime. And now we would like to know which regions of spacetime are accessible to infinity and which are not, and how many connected components does the infinity have. So we will start by introducing conformal compactifications. So ultimately, conformal compactifications are an important tool for us. So recall that conformal transformations, so let's say that we have a manifold M and a metric G. The conformal transformations then go to define the new metric on the same manifold, which is related by a conformal factor omega, capital Omega, to the previous one. So the conformal compactifications, therefore, they change the distances, and in particular, they can bring the points infinitely far away into a finite region so that we can draw them on a diagram. At the same time, they don't change the angles, and neither do they change the causal structure. So the idea is, therefore, that by picking an appropriate omega, we can make the asymptotic boundary of the spacetime at finite distance, which will also potentially allow us to find new regions of spacetime, which were not accessible to us before. So, in fact, we will have a different manifold. I'll write it as M bar. Which may contain new geometric regions. So let us study with an example of the Minkowski spacetime. So, as you recall, the metric on the Minkowski spacetime can be written as minus dt squared plus dr squared plus the metric on a two-sphere. So here I'll write the index s squared so that we don't confuse the metric and the conformal factor omega. So it's important to keep trace of the range of the coordinate variables, because, well, here we will be redefining the manifolds, and we define the manifolds for their charts, so through the ranges of their coordinates. So extending the ranges of coordinates will allow us to probe the asymptotic regions. So we have that time takes real values, and the radius is a non-negative function. Good. So now let us introduce the ingoing and outgoing coordinates. So we introduce u equals t plus r, v equals t minus r, and therefore we have that minus infinity u less or equal than v, which is less than infinity. And this inequality comes from the radius being non-negative. So then the metric is ds squared minus du dv plus 1/4. So we indeed have u minus v squared. Then we have seen these two transformations before. Now let us define something new. Let us introduce the new coordinates that will bring the asymptotic region at a finite distance. So we do this through the tangent function, which brings the infinity to pi over 2. So then the metric is ds squared 1 over 2 cosine p cosine q squared times minus 4 dp dq plus sine squared of q minus p metric on a two-sphere. So in this case, p and q vary from minus pi over 2 to pi over 2. Good. So now we introduce the conformal compactification. We naturally have some prefactor which we want to cancel. So let us define this as omega minus 2. And we've got that on a step 4. We've got g equals omega squared g equals minus 4 gp dq plus the spherical part sine squared q minus p d omega s2. Finally, it's convenient to disentangle p and q into the time-like and spatial-like coordinates back. So we introduce the t equals q plus p, and this will belong to minus p to p, and we introduce chi, which is q minus p, and it's actually a periodic coordinate. It is defined from 0 to pi. It's not defined in pi because the coordinate is then periodic. And the metric is g bar equals minus dt squared plus d chi squared plus sine squared of chi d s2 squared. Good. Now, observant listeners would then see that this is actually nothing but the metric on a three-dimensional sphere. So where again we have chi changing from 0 to pi. We then have the metric on the two-sphere with the coordinates given by theta and phi, theta changing 0 to pi and phi changing 0 to 2 pi. And these coordinates are related to earlier coordinates by a corresponding change of coordinates. So in total, we have that the conformally compactified Minkowski is a direct product of a time interval times a 3 sphere. Now, let's plot it. let us plot it as a part of a larger spacetime. So let us draw an infinite cylinder. Infinite cylinder, this is the time, and the spatial cross-section of the cylinder is the S3. So, well, in a usual two-dimensional cylinder, the cross-section is S1, the circle. Here we have a three-dimensional sphere. This geometry is called the Einstein static universe. So, also abbreviated as ESU. Now, let's see how the compactified Minkowski fits into the bigger picture. So let's have it as a zero value, and let's have it as pi, and let's have it as minus pi. So the coordinate chi then runs from 0 to chi equals pi here. We then have the geometry defined as follows. The chi equals pi is the point where the geometry must merge. So the chi equals pi is the chi equals pi is the point where the geometry reduces to a point, and the whole of the compactified Minkowski is defined on the segment of the cylinder. So the Minkowski spacetime itself belongs to the interior. So let us see what the different parts of the geometry correspond to. To do this, it's convenient to project it on a plane. Such that we get a diagram. Where this is this point, time equals minus p, is the origin of time. So this is the point where if you have a complete evolution of a time-like matter, this is the point where this evolution will start. So let's call this point beginning of time. Let's call this point to be past time-like infinity. Similarly, if you have a complete evolution of time-like matter, then this is the end of times. And this is therefore the future time-like infinity. This point is effectively infinitely remote. This point is infinitely remote, and it cannot be reached by any causal matter starting in a physical region. So we will call this region space-like infinity. Spatial infinity. Now let us look at the light curves, at the light rays. So the light rays on this diagram, the light rays would go as 45-degree lines. So if you have a light ray starting here, it would then go until it reaches psi equals 0, and then it would keep going till it reaches the asymptotic. This is what a trajectory of a complete light this is what a trajectory of a complete light-like geodesic will look like. So if you project it, we would see that light-like curves, that radial light-like curves, correspond to the straight lines. So we have them starting at some region in the past, at some past null infinity, going into the center of the space-time, and then exiting again in the asymptotic region. So we therefore call this surface, we therefore call this region I minus for the past null infinity, and this region, we'll call it I plus for future null infinity. So this naturally gives us a setting for the initial value problem. So if you specify all the initial data at the past infinities, that is, we specify the chronal, the time-like matter at the past time-like infinity, and the null data on the scry minus. This letter is called scry at the past null infinity. Then we should be able to trace the evolution of this data through the space-time, and then find the S matrix and the future null infinity. This gives a start to the main problem, which is studied in the celestial holography, which is also called the flat holography. This is not the topic of our lecture. This is not the topic of our lectures. So let us continue with drawing the diagrams. Okay, so the next diagram we would like to draw would be the diagram for the two-dimensional Minkowski spacetime. So everything should be very similar here, because, well, except that we don't have the sphere. So we should get this triangle. Well, in fact, we get something else. So what is a two-dimensional Minkowski? It's time coordinate times spatial line. And the spatial line has two ends. While in high dimensions we would have we would have 1, 2, and high-dimensional spheres. In two-dimensional Minkowski, we have a zero-dimensional sphere, which is just 2 points. So we will have 2 asymptotically flat regions. Therefore, the diagram looks as a square instead of a triangle, where the 2 asymptotic regions would be, again, we call this right future null infinity. We call it right spatial infinity, right past null infinity, and this is the time like future and past infinities are the same, and we have the same structure on the left hand side. So by the way, this letter in literature is usually called scry, and if I write it honestly, it should look something like this. Not entirely dissimilar from I, but definitely a different letter. Okay. So now let us draw something more interesting, the Kruskal spacetime. So it is a good exercise to reproduce the procedure we did for the Minkowski spacetime for the Kruskal. So we can then again define, the coordinates P and Q, this time for the Kruskal U and V. Use tangent P, V is tangent of Q, and again we have omega given by 2 cosine P cosine Q, and so on and so forth. So in exterior we should get something of a Minkowski. Let's see how it all fits together. Recall the Kruskal diagram. The Kruskal diagram was defined with respect to capital U and capital V, which are also used as part of one of the many coordinate transformations to give us the compactification. So the total structure, the total Penrose diagram, would then be a completion of Kruskal diagram to infinity. So this is how it looks. So this is the external region. This is the black hole region. Number 3 is the white hole region. And number 4 is a second asymptotically flat region. So as you can recall, the Kruskal spacetime has 2 asymptotically flat ends. So this is area equals 0, and this is the infinity in the future and in the past. In the future we have a black hole, in the past we have a white hole. So in this spacetime, we have 2 sets of both. 2 sets of everything. So we have the past time like infinity given by these 2 points. We have the future time like infinity. We have 2 spatial infinities. Okay, let us denote these values with a prime. And we have scry plus and scry minus. And again, scry minus prime, scry plus prime. as usual, the light-like geodesics go as straight lines to infinity. Now, finally, let us draw the Penrose diagram for the gravitational collapse to a black hole. So, let's have the spherically symmetric collapse. Again, we have matter well defined at first, until at some point the black hole forms. We have a horizon, and it all ends in a singularity. So we have the singularity, we have horizon, and we have future and past time-like infinities and future and past null infinities. This is the r equals 0. Okay, now let us formalize our knowledge and let us give a definition of what we would like to call as asymptotically flat spacetimes. So we want to define the asymptotically flat spacetimes as spacetimes which resemble Minkowski spacetime at the infinity. So let us now write the following long definition. So we would call a time-orientable spacetime to be asymptotically flat at null infinity if there exists such a conformal compactification m bar g bar such that, first of all, there exists a positive function omega on M such that m bar g is the extension of the given spacetime. Is an of then the second point is that M can be extended to the manifold with boundary. Manifold with boundary, which is a subset of which is included into this big M bar. Manifold with boundary means that instead of the usual so in the usual definition of a manifold, while we can also have open chuds, we're also allowed to have chuds where we map not to the whole R but only to its half, or sometimes even to its quarter if it's a corner of the spacetime. Good. Then we of course want omega to be well behaved. So it's not just positive, but we also have that omega at the asymptotic boundary is 0, but its derivative is non-zero there. So therefore, we can treat omega. Therefore, we can treat omega as a function of on manifold with boundary. Well, we have that. Well, we also want the boundary of the manifold to be a disjoint union of two regions of scri plus, scri minus. Two causal components each is diffeomorphic to R times the two-dimensional sphere. In high dimensions, we would of course demand this to be diffeomorphic to high-dimensional spheres. And yes, and we also want, we of course want to emphasize that this scri plus and scri minus are future and past null infinities. So we therefore have that no past or future causal curve past the future directed causal curve starting in M intersects scri plus or scri minus for future directed ones. So indeed, scri plus is the future. And scri minus is indeed the past. And finally, we would like to see that scri plus, scri minus are complete. We will see that scri plus and scri minus, they are in fact null hypersurfaces. And by saying that they are complete, we would mean that their generators, which are null geodesics, are complete in a sense that their affine parameter runs from minus infinity to plus infinity. So we would mean that this is that their generators are complete. Good, so this is it. Notice that we haven't included the spatial infinity. I note in the definition because, well, even for some very well-behaving spacetimes like Schwarzschild, Kruskal spacetime, I naught is not that well defined. For example, you would have, if you plug in R goes to infinity, you would get actually R goes to infinity, and if you take the space-like limit, you would actually get you would find that the metric there becomes singular. So therefore, we define the spatial infinity as some point which is not included in the construction. We basically avoid it by saying that the null infinity is a disjoint union. Okay, so this is definitely a very remarkable definition, which definitely covers a lot, of properties of the spacetime. So the points 1 to 3 state that the conformal compactification is well defined, and 4 and 5 give more details about the structure of the infinity. So this is, of course, a very remarkable definition, which states both that the conformal compactification is well defined, that's in the points 1 to 3, and also gives us the idea how the infinity of the spacetime looks like. That's the second part of the definition. So essentially, if you draw it as a diagram, it means that asymptotically flat spacetime will look like this at the infinity. There can, of course, be multiple asymptotically flat ends, like in Kruskal spacetime, and we don't know what happens here. So we can complete it to Minkowski spacetime, or there can be some singularity or some more complicated structure that we'll see in the next lecture. So that's what we have. So naturally, the question is that in these lectures we have already defined some notion of asymptotical flatness. So if you recall the lecture 4, when we were discussing the initial value problem, we have given the definition of asymptotically flat initial data, which was local. It was done through the decay rates of the metric functions and its derivatives at the infinity. The question is what is the difference between these definitions and are they even related? So there are two important points here. First of all, well, the asymptotically flat initial data is a local definition. The local decay rates, while state that at this particular part of the space-time the metric goes to Minkowski, it does not give to us the global structure of the infinity. So in other words, the asymptotically flat initial data would correspond to local asymptotically flat spacetimes. That is, the spacetimes that resemble Minkowski only at some part of its asymptotics. While here we have given a global notion. So in the literature, the spacetime satisfying this or a similar definition would be called globally asymptotically flat spacetimes. Okay, so the second point is more practical. In the local definition, we were given some particular decay rates, which is useful to directly constrain the metric and metafields if included. So now we will show that this definition, in fact, contains sufficient information such that, well, together with Einstein equations, but we can actually derive these decay rates from this definition. So let us start. Okay. So first of all, the conformal factor is actually given up to the transformation by the function omega, which is positive and non-zero. So omega is smooth and omega is greater than 0 at M and its boundary. So effectively, this is the gauge freedom, which we will now partially fix. Okay. So this is essentially the gauge freedom, and it is convenient to fix it to fix this gauge freedom such that the covariant derivative with respect to m bar of this function omega is 0 on Scri plus. We can always do this, in fact, and this was shown in Hawking-Ellis. So in showing that we can always do this, we had to use the knowledge from Einstein equations or also the equations of motion for the matter, if it's present. Now let us introduce the one form, which is the derivative of the conformal factor omega. And this, of course, is normal to Scri plus. So using this So using this gauge freedom, first of all, we can show that n squared at square plus is 0. So that we have a null hypersurface. And we can also show that and it also follows that d bar mu and nu on square plus equals 0, which in particular means that the chain rate of the null hypersurface is affinely parameterized. Now, let us introduce the new coordinate u along the flow of the vector field related to n mu by the conformal metric G. So let us define n mu given by G bar mu nu n nu, and let it be given in our chart, and let it be given in our chart by d over dq. So in total, we have the following construction. We have this chi plus, and the n mu is a vector field tangent to it. While n is the normal. And if you have a chart defined on square plus, that is coordinate u, and the coordinates on a two-dimensional sphere, then we can extend them into space-time to omega u theta phi. So in total, this construction is very much similar to the construction of a Gaussian null coordinates. Okay, so far we have defined a chart in the vicinity of the future null infinity, which is a null hypersurface. Let us now write down the metric. So the future null infinity, these coordinates, is at omega equals to 0. So the metric is given by 2 du d omega plus the metric on the spatial cross-section, which is the two-sphere. So this is dt squared plus sine squared theta d phi squared. Now the metric on the whole of the space-time is then minus 2 du g 1 over omega. So where I have included omega minus 2 into the differential, plus omega minus 2 times d omega s2 squared, plus terms which are smooth in omega. Which is smooth in omega. Now, this should resemble a flat metric if we go from omega to radial coordinate given by 1 over omega. So let us define the asymptotic radial coordinate given by 1 over omega, And we have G given by minus 2d u dr plus r squared d omega s2 plus terms smooth in 1 over r. Okay, so effectively this is it. These are the decay rates for the metric. So if we were more cautious about the details here, we could then improve the gauge. And identify some of the subleading components with some of the fundamental properties of the space-time. For example, with the mass, the angular momentum, and so on. So we will give the definition of such conserved currents, mass, angular momentum, charge in the future lectures. Okay, so now, after all the preparatory work over 7 lectures, we are ready to give the definition of the black hole. So, what do we want to call the black hole? Well, we started with black holes being the endpoints of the gravitational collapse, but now we'd like to follow a more colloquially known thing. The black holes are regions of spacetimes which the light cannot escape. Or more formally, they are the regions of asymptotically flat spacetime from which it is impossible to escape to infinity, the timeless infinity or null infinity. So let us give the definition. So let M and G be asymptotically flat at null infinity spacetime. So then the black hole region B is therefore given by M excised by M with the intersection so the intersection of M with the causal past of Scri plus. So again, a black hole is the region which does not belong to the causal past of the future null infinity. We cannot send a signal to future null infinity. We are intersecting it with M because the definition of Scri plus, was defined for the conformally compactified spacetime M bar and not with the M itself. So we can then define the black hole horizon. So we will define the future event horizon H plus as the boundary of the black hole region. Or similarly as the intersection of M with the boundary of the causal past of the Scri plus. We can give similar definition for the white hole region that we have seen in Kruskal spacetime and for the past event horizon. So So a white hole region is a region from which it is impossible to receive a signal from infinity. And the future and the past event horizon is the boundary of the white hole region, or similarly, together with the boundary of the causal future of scry minus. So this is the definition we can work with. Of course, it has some technicalities. For example, For example, if we cut out a point from Minkowski spacetime, we may have black hole regions to be non-empty, but we would prefer to work with complete asymptotically flat data, such that these technicalities are out of our scope. So, in Kruskal spacetime, we have naturally seen both the black hole and the white hole regions. So, in Kruskal spacetime, the black hole region is the region 2, which is bounded by singularity, and the future event horizons. The white hole region is also bounded by the singularity, this time the past singularity, and by the past event horizons. Now let us give the following definition. So, an asymptotically flat spacetime Mg is strongly asymptotically predictable if the exterior is globally hyperbolic. So in other words, if there exists an open region, V bar, belonging to the conformal quantification of M, such that the boundary of M and the causal past of the scry plus belongs to the V bar. So in other words, the exterior belongs to the V bar, and V bar G bar is globally hyperbolic. So this definition has a simple consequence. The black holes cannot split in two. So again, let Mg being strongly asymptotically predictable, and let's have two Cauchy surfaces And let's say sigma 2 lies to the future of sigma 1. So we have sigma 2 belongs to the sorry, the indices should be below, belongs to the, actually not just causal, but the time-like future, the chronal future of the sigma 1. And let B be the connecting component. And let B equals the intersection of the black hole with sigma 1 be connected. Then we naturally have that J plus B belongs to sigma 2. So the causal future of the region B belongs to the sigma 2 and is contained in a single connected component of intersection of the black hole with sigma 2. Okay, so let us draw the picture. So we have B given by the intersection of the black hole region with the first Cauchy surface sigma 1, and we have its image in sigma 2 given by two disjoint O and omega prime, given by omega and omega prime, which are the neighborhoods containing the image of B. Well, the proof is more or less straightforward. Okay, so the proof is straightforward. So since the space-time is globally hyperbolic, every time-like curve which crosses sigma 1, it first of all crosses it only once, and secondly, it will cross sigma 2 exactly once as well. So if you have a family of time-like curves, if you have a time-like congruence starting from sigma 1, they effectively define the diffeomorphism. So if you recall, they define the diffeomorphism. So if you recall, the global structure, the global topology of the global topology of globally hyperbolic spacetime is a direct product of time times the topology of the Cauchy slice, and this is the consequence of it. We have the global diffeomorphism given by any time-like congruence on sigma 1, which gives us the structure of the spacetime. So, in particular, under this diffeomorphism, we would have the image of B, which belongs to sigma 2. However, the B is connected, and therefore, since it's a diffeomorphism, the image of B must be connected as well, which immediately contradicts the assumption that it is disconnected. Okay, so in other words, if we have a connected image, or if we have a connected image of horizon at sigma 1, its image at the future Cauchy surface must also be connected. Then its image at sigma 2 must also be connected. In other words, the black holes do not split. We have many times emphasized the two essential features of Kruskal spacetime. That is the central singularity and the event horizon, which hides it from asymptotic observers. In the previous lecture, we have shown that singularity formation is a generic process in theories of gravity. But what about the event horizon? So are naked singularities natural in GR? So if you want to think about the gravitational collapse which leads to a naked singularity, unprotected by horizon, we may be prompted to write the diagram. We may be prompted to draw the diagram of something like this. So this will be the scry plus, scry minus, and this is the center of the space-time, r equals 0. So at first we would have it as a regular point, but then as the matter collapses, as the stellar matter collapses, we end in central singularity. So the initial data surface, so we can choose the initial data surface as this. So we can choose the initial data surface as this, and then study the complete evolution. Well, this diagram is in fact very misleading. As we have studied in the previous lecture, the naked singularity, for example, the negative mass Schwarzschild, is not globally hyperbolic, and its predictability is limited by the existence of the central singularity itself. Well, for example, since the singularity is not protected by the event horizon, we may have light rains. We may have light rains emanating from it at any point in the future. So, therefore, in this diagram, we would actually have the Cauchy horizon given by this, given by the line which starts at the moment when the naked singularity formed, and all the way to scry plus. And now, since we have the Cauchy horizon, we have actually lost the predictability of the data in the exterior region, and we do not know what happens in the inside. Now, we have made this diagram more physical by removing the naked singularity. This diagram, however, is still pathological. So first of all, there exists the Cauchy horizon, which limits the predictability of the spacetime. So in particular, the strong cosmic censorship is violated. And if these processes are generic, we are in a big trouble. We need something else than rather than general relativity to predict the gravitational evolution. Secondly, this spacetime is actually not asymptotically flat, because the scry plus is limited. Because the scry plus is limited, it is cut at a finite value of the affine parameter. So we have scry plus is not complete. So again, naturally we would expect that. In a generic gravitational collapse, such pathologies should not form. This leads us to another cosmic censorship conjecture. This time the weak cosmic censorship conjecture. So let the space-time be geodesically complete, let the initial data be geodesically complete, asymptotically flat initial data set. So this was the same assumption that we had in strong cosmic censorship. Now, let the matter obey hyperbolic equations of motion and satisfy the dominant energy condition. Then, generically, the maximal development of this data is asymptotically flat spacetime that is strongly asymptotically predictable. So in other words, that the exterior of the black hole is globally hyperbolic spacetime. Okay, so first of all, we are speaking about the maximum development. This is because if the evolution is partial, then there will exist some boundary of the predictability, some local Cauchy horizon, which would of course limit the strong asymptotic predictability as well. Secondly, again, as in the strong cosmic censorship conjecture, we use the word generically. This is because there are some fine-tuned examples where weak cosmic censorship fails. So, in early 90s, first by Christodoulou, who did it rigorously, and then by Choptwick, who studied it numerically, there have been examples of the spacetimes, there have been examples of the gravitational collapses, which lead to a naked singularity. And the event horizon did not form. Those, however, were extremely non-generic. First of all, from all the set of asymptotically flat initial data, this naked singularity initial data was actually a set of measure 0. In other words, Christodoulou parameterized his data by Christodoulou has parameterized general asymptotically flat initial data by a number of continuous parameters, and these pathological developments were related only to some fixed values of these parameters. So secondly, this asymptotically flat initial data was not actually smooth. So the weak cosmic censorship, although somewhat similar to the strong cosmic censorship, is an entirely independent statement. And it is not a weaker version of the strong cosmic censorship. So, in particular, one can come up with the diagrams that would be true for the weak and wrong for the strong, and vice versa. So let us draw the following diagram. So let us draw the following diagram, where these are scribed pluses, and let this be the surface in which we define the initial data. So let this be the event horizons, the future event horizons, and let these be the Cauchy horizons. So of course this space-time is perfectly fine with weak cosmic censorship. So, but the strong cosmic censorship is of course violated because we have the Cauchy horizons. So this diagram is not arbitrary. We will see it in the next lecture where we'll speak about the charged black holes. And for the second counterexample, we can take a cosmological model of a big crunch, that is the time reversal of a big bang, where the universe ends in some kind of final singularity. So here we would have the future null infinity. We would have the future null infinity incomplete and bounded by some value. But this geometry admits a Cauchy surface and is globally hyperbolic. It's globally hyperbolic. So, in other words, the strong cosmic censorship conjecture is satisfied. There are no Cauchy horizons. But the weak cosmic censorship conjecture disagrees with this diagram. Verifying and checking both cosmic censorship conjectures is an important open problem in mathematical GR. So far, there have been extensive numerical evidence that the weak cosmic censorship should hold in general. So far, it has been done for different kinds of scalar matter, as well as for the electromagnetic and Young-Mills fields. So in the next lecture, we will turn back to particular examples of black hole spacetimes. So this time, they will be black holes with charge and rotation.